Good evening and welcome to this last lecture. I'm going to recall what we have done last week, even if I'm not going to use it at all today, but it's good to refresh your memory. And then I will just make a few administrative announcements. So last week we looked at the configuration model. It's a model of random graph, but it's different from the one we have seen before, because in this model, we fix the degree distribution. So you start with a degree distribution, so a distribution based on K in N, and you fix the number of vertices you want, and then you create N times Pk vertex having K stubs. So this is for 3. A stub is a half edge. So you create N times Pk vertex with K stub like this. And okay, you do many, some with 3, some with 2, and so on. And then you connect these stubs at random. So there is still some randomness, but the degree distribution is given. All right. And then, of course, you may have loops, because sometimes you're going to connect like this. But it turns out, and we computed, the density of loop in your graph is going like 1 over n, which means that the probability of having one loop at a given vertex is going like 1 over n. And you can also discuss the density of double edge, because we can be in this situation, but also this decay as 1 over n. Then we also discussed something which is a little bit surprising. If you start from one vertex and move to another one and look at the degree distribution of this new vertex, it turned out that the degree distribution of this, I call it a neighbor because it is a neighbor of somebody, is different from the degree distribution of an arbitrary vertex. And one way to say it with words, and probably it's better in this way than what I said last time, is your friend has more friends than an arbitrary person. Because it's not only because you are his or her friend, but because it means it has already one connection, while it's possible to have some vertex or some vertices with no connection at all. And in fact, the correct statement is that the expectation of a degree of y connected to x, so you start at x and you go up to y, and then you look at the degree distribution of y is bigger than the degree distribution of an arbitrary x. Right. We also computed the configuration, what's the name? C. Correlation? Yeah, correlation coefficient. It goes like 1 over n, which for many applications is still decaying too fast, but a clustering coefficient. But still, so for some application, it's not good, but okay, that's it. That's life, or that's this model. And the last thing I presented is the use of this configuration model for finding or for the detection of community. And I explain what is a community. It's not very precise, but still you would like to find in a graph if you have some parts which are more tightly connected than other parts. And I gave one way to do it precisely with this configuration model as a reference. It's for two communities. You define a matrix with, you start with the adjacency matrix of your graph. You subtract this, which is related to the degree of any vertex. And then I don't want to do the full construction. Then we consider a vector made either of 1 or -1 at each entry. It has length square n. And the problem ends up in finding an extremum about this quantity. So this B applied to L, and then product with L transpose under a constraint. Of course, you cannot work on this if you keep L only with the value 1 and -1. So we have to put it in Rn. But once we are in this framework, we have this Lagrange multiplier, which tell us what to do, and the problem then reduced to an eigenvalue, eigenvector problem. And if you extrapolate the solution you are going to find, it's an approximate solution for the two community problems. So you can isolate two communities. It's not perfect because we have to go from a vector in Rn to a vector of this type, but still it's better than nothing. Now, some administrative things. If you are from Nagoya University, you are familiar with this. Every semester, you have to fill some survey or questionnaire. Please do it. It takes you only a few minutes, but for us, it's important because we receive an evaluation based on this. There is a problem with the server of the math department. I cannot upload any new file. So I hope it will be solved. I already mentioned it to the person in charge, but it means I cannot upload new reports and I cannot change the version of the notes. I hope I will be able to do it in a few days. So please be patient. No, apparently you can still download files, but I have no way to put anything on it. And I cannot change this, but the person in charge has not been able to solve the problem for 3 days. Then finally, deadline about reports. I would appreciate if we can finish everything within the next 2 weeks. So please, I'm not saying that it's a completely fixed deadline, but please try to do it. It's also better for you. I propose, if you're interested, to organize some oral exam. Please let me know if you want to take this opportunity. It can only improve your grade. I'm not going to give you a bad grade if you take an oral exam. And about grades, I have this policy. I never give any grade to the administration before discussing with you. So don't be surprised if at one point I say, oh, you have submitted only 1 report. So I'm planning to give you this grade. If you want to improve, you have to produce 3 more reports. Let's heavy do, this is for you.
Oh, no.
Yes, because you're speaking so much. So don't be surprised if I contact you, and it's not really a negotiation, but if you want to improve your grade, yeah, it's still possible. Do you have any question or remark? Okay, so sorry for the server. I hope, please double check in a few days, and if you don't see anything new, it simply means that the problem has not been solved yet. All right, so today we discuss a last topic, which is about epidemics on graphs. It was a very hot topic very few years ago. It's still an important topic. I give you only a very few information about this. Still, it's better than nothing. So this is the last chapter, number 12, epidemics. But the first section, there is no graph. So this graph will come just the next section. So this is about basic model and basic ideas. Everything is very simple, but of course we can, from these basic ideas, you can go up to much more complicated models. So what is a compartmental model? It's a model made of compartments. So it's a model consisting of various we have several compartments, and each compartment, it contains the same kind of person, which contains a homogeneous population. So I will directly give you an example, the most basic example. you have three compartments which are called S, I, and R. Three compartments. So this is an example, but this is a basic example. You have three compartments. S is for susceptible. This person can get a disease. They can get disease. Then you have the I, which are the infected. They are infected. And R is for those who have recovered. These names, SIR is standard, it's not from me.
By recovered, you mean still not spreading the disease? Or...
Yes, they cannot infect anybody anymore. Now, I will mention sometimes these guys go back to S if they did not get any immunity. Sometimes they are immune. So it depends on the model. For now, I don't speak about this. I just say we have three compartments, SIR. This is really at the root of all these models. SIR, you can see this at many places. So in each compartment, you can have either you have peoples. So it means either you count how many persons you have in each compartment, or you have densities, which mean a real number such that the sum is going to be 1. So we have two possibilities. So each compartment represents or contains, I should say, either some persons. So it means this is an integer or a fraction of the entire population. Which means it's a number between 0 and 1. But what we have always, in the first case, we have S plus I plus R is the total population. If you count the individuals, you get the total population, or S plus I plus R is equal to 1, depending on which picture you prefer. Right? And of course, we need a dynamic. We need to say about the evolution of this system. So the evolution is given by an ODE. What is an ODE? It's an ordinary differential equation. The dynamics is given by an ODE, which means ordinary differential equation. It means it's a differential equation, but depending only on time. The derivative is only going to depend on time. This is a difference with a PDE. Okay, so the first example or the very first model is what is called the SI model, where we have only susceptible and infected. So once you are infected, you remain infected. This is the simplest situation. So your population is only divided into two categories or two compartments only. S compartments. S and I. No, you cannot recover. So I'm going to use a variable. I have to be a little bit careful. I'm going to use S, and I don't want to use I. You will see very soon why. So I'm going to use this, which is iota. It's an I without a dot. Why without a dot? Because I want to use the dot for derivative with respect to time. So this is a iota. Probably I will sometimes put a dot, but I shouldn't. Please correct me. So this S on iota are function of R with value. I take the second picture, 0, 1. The parameter here is T. And they satisfy that S of T plus iota of T is always equal to 1. I'm going to characterize these two compartments by these two variables, S and iota. Now, what is the dynamic? So it's a certain model. The dynamic is given by this S dot. So the derivative with respect to T, it's common to put a dot and not a derivative. It's part of the history. But this is nothing but ds over dt at time t is given by minus beta s of t iota of t. This is a model. It says that the change of susceptible is given by a coefficient, and this coefficient is called the transmission coefficient. So beta is called the transmission coefficient. So the derivative of s with respect to t is given by minus beta times s times iota. And why it's quite natural? Because the more infected person you have, the more likely a susceptible is going to get infected. And the more susceptible person you have, the bigger this number is going to be. But it's a model. If you don't like, if heavy do, you're allowed to put a square if you want. This is a heavy do model. But people do start with this usually. Beta, yes, beta is a positive. It can be 0, but of course it's not interesting if it is 0. And of course we need a second equation. And now you understand why I didn't want to put a dot. Derivative of iota has to be equal to beta s of t iota of t. Because people leaving S, they have to enter somewhere, and that's why you have the same thing. All right? Okay. And of course, this system is simple in the sense that since we have only two variables and they sum up to 1, you can rewrite this in an even simpler form. So by this equation here, we get. I'm not going to write the t all the time. I will forget it. But we get the derivative is minus beta s times 1 minus s, and iota prime is beta iota 1 minus iota. Let's see. Because the sum is 1. And these equations are called logistic equation. And of course, we know the solution. The solution is given by iota of t is equal to the 0 p beta t 1 minus iota 0. Where iota 0 is iota at time 0. You can check, you use this solution. So I give you the solution. You take this solution, you implement it here. Remember, this is a derivative with respect to time, and you check that it's indeed a solution. And it's the only one if you give this initial, this is called the initial condition. And you can even plot this function, and the plot as a function of t. Of course, it has to be within the interval 0, 1. And of course, if you start with 0, if your initial condition is 0, nothing is going to happen. But as soon as iota 0 is not 0, so as soon as I represent, this is a function iota. As soon as it is not 0, you can see that it's going to be like this, and it will converge to 1. So it means as soon as you have an infected person, everybody is going to be infected over the time for this model. All right? If beta is strictly positive and if the initial condition is not 0. This is really the simplest model. If you have any question, you can always ask me. And the same online, if you have any question or comment, you can also interact. I let you do this exercise because of this sum. Indeed, if you try to represent S, S is given by 1 minus iota. So you can indeed plot the population of susceptible. I let you do it. Yes. It's decaying. So it means the number of susceptible is decaying up to, is going to 0. So at the end, everybody is infected. Now already the slide. Second model, which is SIR. So now I'm going to use a 3 compartment. I mentioned that when people recover, they are immune. I take this assumption they are immune. What does it imply? It implies they don't go back to S. Of course, you can change this assumption. You can say they're immune for a certain period of time, and then they go back to S. This is also possible, but the simplest case is when you are immune forever. And for some diseases, this is correct, essentially correct. So we need to write, we have 3 variables, of course. The variables this time are going to be S, iota, and R. They are all from the function of time into 0, 1, and the sum is 1. The sum of S plus I plus iota plus R is equal to R for any time. And what is the dynamic? Again, this is a model. but it's quite natural. Derivative of S is the same as before, minus beta S iota. You leave the compartment S only if you get infected by somebody. Then when you are infected, you either become infected because you have been infected by somebody, or you recover. I will mention it. And recover, of course, you only arrive there when you leave the other compartment, the infected compartment. What is this gamma? Or more precisely, there is an interpretation for 1 over gamma. 1 over gamma is a mean infectious time. This model is not perfect for the following reason. And there is a way to correct it, and Alberto is going to write a report on it. I will tell you what you are going to work on. So why is it not perfect? Because so I think it's understandable. For the same reason, the variation of susceptible is because they become infected. Then in the compartment of infected, you get new people, but people are also leaving, and that's why you have a minus. And of course, in the recovered, people are just coming from the infected because they have recovered, so you have just this factor, right? Now, what is a small problem? The probability of an infected individual, or of an individual infected at time 0, of an individual infected at time 0, an individual infected at time 0, that this person will recover during the interval t and t plus a small delta t, small interval, is given by this expression, which is gamma E minus gamma T delta T. It follows from this differential equation, from the differential equation given by this, the fact that the derivative is proportional to itself. So it means the probability of recovering if you have been infected at time 0 during the interval t plus delta t is given by this. And if you plot this function, it looks like this. You see the exponential decaying. So what does it mean? It means that the probability you recover, it's the biggest one at the very origin, which is not very natural, because most probably if you get cold, your probability of recovering should be like this. You're sick for a few days, and then you start recovering. But this model is very simple, and it turned out that from the very beginning, you are not infected for a very long time, while this would be more natural. And there is a way to correct and to get such a curve, and I will mention it in a few minutes. So there is a price to pay for the simplicity of this model. Nobody is going to die. No, please. I'm a gentle guy. Nobody is going to die. I will speak about the dead in a second. So not very realistic, but not very realistic. But still, it's okay. We can survive. Now, okay. We usually assume that at the time 0, please, we usually assume that at time 0, we have nobody who has already recovered. This is a natural assumption. Then we get, I want to get a solution or partial solution for this. We get from 1 and 3. What is 1 and 3? This is 1 to 3. So what we get from 1 and 3, from 1, we are going to get that S dot over S is minus beta iota. And this is also equal to minus beta. Now I get I from the third equation. So it is R dot over gamma, and I'm going to write it as beta over gamma R dot. This is what I wanted to get. But I can integrate this equation. I get that logarithm of S evaluated at logarithm of S of t evaluated at t and at 0 is minus beta over gamma times R of t evaluated at t and at 0. I just integrate on both sides. But look, this is equal to beta over gamma with the minus sign R of t, because of my assumption that nobody has already recovered at time 0. And now I can take the exponential on both sides. So I get a certain relation. I get that S of t by taking the exponentials. You get that S of t is initial condition at 0, E minus beta over gamma R of t. So we have a relation between S of t and R of t for this model. Okay. And now it's no more visible, but I insert this from the relation R plus S plus I iota plus R is equal to 1. We get from 3. So I need to write it again. What was 3? 3 was R dot is equal to gamma iota. I can express iota with this line. So it means this is gamma times 1 minus R minus S. But S is here. So this is gamma times 1 minus R minus S0 E minus beta over gamma R. And now you can observe you have a new differential equation only in terms of R. Derivative of R is a linear term in R, an exponential term in R. Right? Now, heavy do homework for you. Please solve this equation. Then you will not speak for a long time because there is no solution. There is no simple solution. There is no explicit solution, but still we can do it numerically. I let you study it if you want. So there is no explicit solution. No explicit solution for this equation. However, what is expected and what we can still say, we can expect that the derivative with respect to time of R goes to 0 as t goes to infinity. Number of recovered person, it will just reach a constant because it's it's an increasing number. It's upper bounded by 1, so it can only reach something, and its derivative can only be 0. You have no other choice. So this is expected, but it implies that now I use it for this. It implies that R at time infinity, replaced by infinity, is equal to, okay, sorry, this is 0, so you put it on the other side of the equality. So it gives you 1 minus S0 E minus beta over gamma R of infinity. You get, because this is 0 and you just solve it. Oh, we have already seen an equation of this type. We cannot get R0, but when we discuss the giant component, we have seen a way to get an idea about the solution graphically. I mean, sometimes graphics are very useful. So this has been studied already. Studied for the giant component. When I discuss the giant component in the GMP model component, we studied this. And in fact, there are two situations. There are two situations. One is for beta over gamma bigger than 1. If you plot this, there exists a R infinity smaller than 1, which is equivalent to S of infinity bigger than 0. I mean, I get this simply by doing the same picture than we did for the giant component. And so if you take this information, what you're going to get, this is 1. If you start with, so we have 3 curves. I'm going to represent 3 things on one picture. One is the susceptible. The number of susceptible is going to do something like this. This is for S. And of course, the axis is T. Then you have the recovered person. No, yes. It's going to do something like this. It's not reaching this line. And you have the infected, which is going, of course, my picture is not perfect. It's going to do something like this. The blue one is I, or J, and the red one is S. Yeah, sorry. My picture is not perfect because the sum of these 3 curves should be 1. So probably around here, this is not perfect. No, it's okay, not so. The blue one is going to 0. The S is going to a certain fixed number, and this one is going to the complement. Okay. So be careful. If you do a picture, do it slightly better. The sum everywhere, you should have this relation. So this is the first case when beta over gamma is bigger than 1. The other case, which is simpler, when it's strictly smaller than 1. So when beta over gamma is smaller than 1, you start at I0, and I0 is simply, I will use the same color. I was blue. It's simply decaying to 0. The infected, so we have 1, this is 1. The infected, it's starting just below, but it's just going to decay a little bit and go to constant. And the recovered is going to do something like this. I hope, yes, it's correct. This is susceptible and infected. iota. You can do the plot also for beta over gamma is equal to 1. I don't know the answer, so I let you do it. Yes, any question? Not in this model. Why there would be oscillation if after recovering you can go back to susceptible. But if you think about it in your equation, because the recovered are just accumulating, the susceptible has to decay. There is no other way. So you cannot have oscillation in this model. But it's a good point. As long as you do not let people go infected again and again, you cannot have oscillations. But of course, there are models where you have oscillation. So the coefficient beta over gamma is called the basic reproduction number. You have probably heard about this reproduction number. It's often denoted by R0. And we know that the threshold value is 1. And why? Because we have clearly a different behavior between what happened on the right and what happened here. In this case, we are going to say that, yes, an epidemic took place, while there no epidemic took place. So this is the epidemic case, epidemic situation, while here we have simply a decay of the infected, the number of persons. All right. Any question? There are plenty of models on internet where you can just give these two values, give an initial condition, because somewhere the I0 is, it's a value here, and it plots you the evolution, even though there is no explicit solution, but it's easy to implement a numerical solution. So you just Google SIR model and simulator, and you find plenty of solutions. I just want to mention other models. And in the notes, I gave a picture related to COVID-19. So many improvements. So let me mention a few. The first and natural one, and I already mentioned it, is when R can go to S again. So this means no more immunity. After a certain time, you can implement a way to stay in R for a certain time and then go back to S, no more immunity. Then you can also implement a vaccination. So have a compartment for the vaccinated persons. So you can take into account vaccinated persons. And maybe this vaccinated person can still be infected, but with a different rate. This is what happened. You are less likely to get the disease. Or you can also speak about the hospitalized, because people in hospital may not propagate the disease anymore, or they are going to die. Indeed, you can add the death or the dead person somewhere. You can also add the babies, because if you do a model which is going to run for a long time, the population can increase again. So you have to take it into account. There is also this compartment which played a role during the COVID, exposed, but no symptom yet. But still you can infect, but there is no way to know that you can infect other people because you have no symptom. So you can add plenty of compartments, add some constant in between these different compartments. And I put a picture with 21 compartments. For the COVID-19, there was such a model. Yes.
If you have disease which you might recover from, if you have no compartment.
Yes, in the very initial model SI, you are infected forever. So you can run this model, yes. I hope this doesn't take place, but yes, you can really, in fact, it's quite easy. You do some compartment, then you decide the flow, how you go from this compartment to another one. You need to make sure that nobody's going to disappear. And then you have a big system of OD. Now, for you, Alberto, you can study what is called the SI power n R model. Study SI n or K depend R. So what is it? It's still a SIR model, but you have different compartments for I. And why it makes a difference? It's for the graph here. Remember, I show you that in the initial model, we have this distribution for the time of being infected. If you put several compartments I, it turned out that the sum, the trick is the sum of n exponential distribution becomes, maybe you know, it becomes a gamma distribution, is a gamma distribution. So if it's a gamma distribution, and the gamma distribution has the shape I've shown before. It has this shape, which is better, because it's more natural. You keep the disease for a certain time, and then your probability of recovering is bigger. So you can model this yellow curve by considering that you go from S to I1, and then from I1 to I2, then you go to I3, and so on. You do n independent infected situation, and then you recover. But because they're independent, you are going to get a gamma distribution, which is slightly better. And you can find information about this slightly better model. Simply, you have a sum of n independent exponential decay, and it gives you a gamma distribution. All right, now I will finish with this model. What is a drawback? What is a weak point? Weak point. You see, everything is based on initial condition. And on some constant. I introduce only two constants, beta and gamma, but I mentioned if you do a more complicated model, you will need additional constants, how you go from one compartment to another one. But why is it a little bit too simple? In a real epidemic, not only the initial condition play a role, and these constants, they can be time dependent, which is still fine. You can still implement your model with some time dependent constant, or no more constant, but time dependent constant. The trick is sometimes they are unknown. And for COVID-19, this was the case. So sometimes they are unknown. So what do you do if they are unknown? There are two solutions. There are probably more than two solutions, but one of them is what is called curve fitting or curves fitting. solution or partial solution. One is curves fitting, which means you look at your real data. Suppose you have some real data. You have your model, you don't know some coefficients. So you draw a couple of graphs with these different coefficients and you check which one looks like your data. Or another one, and I encourage you to look at this, is what is called data assimilation. And I know something about this because I worked on assimilation. I worked on this and I gave a course on this. Some of you attended it. What it is, it's really a way to use the daily information and put it in your model and create a kind of loop. You let your system evolve based on an equation, but you also use on a daily basis the data and you compare them and you improve regularly. So once I gave a course on this, maybe I will give it again. This is a method for dealing with this problem. And in particular, you can get what is called the reproduct. I mentioned R0, which is a basic reproduction number, but now you can make it time dependent. And indeed, during the COVID period, knowing this was a big issue as a function of time. So there are plenty of improvements. This is just the basic thing. Any question or remark? Yes. You know, in what I implemented or what I explained is a continuous time. Of course, when you do numerics, your time is never continuous. So you need to discretize the time. But the notion of differentiability for discrete time also exists. It's a difference equation and no more a differential equation. It exists here. Yeah, indeed. For when you do numerics, continuous functions do not exist.
You can simply convert the differential equations into like something like P minus delta.
Yeah, there are ways to transform your differential equation in a difference equation for discrete time, and then you play with the length of your time interval. Depending on what you model, maybe your time interval is going to be 1 second or 1 day if you are speaking about very long period of time. So yes, there is a way to discretize all this with respect to time. Yes, probably. It depends on your mesh. It depends. If you take a time interval which is small enough, you will not see the difference between the continuous time and the discrete time. And in fact, all the simulation that I mentioned, you just write simulator SIR, they are using discrete time.
But with like very small time steps.
Yeah, the time steps are going to be small, and then you can even smooth your function. You do an extrapolation between your dots. All right. So there are techniques, either curves fitting if you don't know all the coefficients, or something more involved, which is called data assimilation. And I'm pretty sure that people have developed additional methods. All right. Now, in the notes, I have introduced a section 3.2, no, 12.2, 12.3. I'm not going to speak about them today. I have no time. So I directly go to 12.4, which is a time-dependent evolution on graphs. Because what I introduced up to now, you had no graphs, but I want to do some model on graphs as well. So I recall that the adjacency matrix, we know what it is. It contains, the entire information contains everything about the graph, everything about the graph, because it contains a connection. So if you have the adjacency matrix, it's the same as if you have the graph in front of you. So I will just use the adjacency matrix. So I define, let's I inside the oh, be careful now, it's really I'm going to use I and j. They are vertices. I don't write xi, xj, I just write I and j for a number between 1 and n, and this is the degree, the number of, sorry, not the degree, the number of vertices of the graph. I use this notation. And let now S index I, iota index I, and R index I denote the probability that the vertex I is, now be careful, it's not the derivative. This is a vertex I is susceptible, infected or recovered. Yeah, I'm sorry, it's in the note, it's probably easier to make a difference between iota and I, so just pay attention here. So you have this, for each vertex I, we have these three quantities, the probability that it's susceptible, infected or recovered, which means that again, Si plus iota I plus Ri has to be equal to 1. And now I need again a differential dynamics. So you should imagine your graph. This is your graph, and you have I, J, and so on. So the dynamics first for SI model, so the simplest one. We have only two states, susceptible and infected. So we have the, let's say, derivative of SI is going to be minus beta, the same coefficient. But now, suppose this one is susceptible. So the infected are going to be the red. What is the probability, the change of probability of S to become, or the point I to become infected? Of course, if its two neighbors are also susceptible, it cannot become infected. So you need to have one guy which is infected, because the transmission can only go through edges. That's the interest. So it means the derivative of SI is going to be given by minus beta SI times the sum J of Aij iota J. Aij is the adjacency matrix. So what does it mean? It means it's the same idea. Your probability to become or to change the variation of susceptibility is related to the S itself. It's related to iota, but you have this relation only if there exists an edge in between. Otherwise, no. Right? So it means we have this relation and the same iota I dot. So be careful. This is iota derivative at vertex I is given by beta iota I times, no. Sorry, it is SI, yes. It's the sum, I need to get the same thing. SI sum J of Aij iota J. It has to sum up to 0. And now for this model, as before, I can use the simpler relation that this is 1, Si plus iota I is 1. So we can transform this in another equation. This system of equation, this is now a system, and be careful, this is for I from 1 up to n. So in fact, you have 2n equations. This is equivalent to the following system. S derivative I is minus beta Si sum j aij 1 minus sj. And the same iota derivative at the vertex I is beta Si sum over j aij 1 minus iota j. Still, you have 2n coupled equations. Why they are coupled? Because look, oh no, in fact, you have 2 times n coupled equations, 2 times n coupled equation. You have a system of n equations involving only the s and a system of n equations containing only the iota. Still, it's not easy to solve it. Yes, you have a question? You can, it's not far from a matrix equation. Is it really?
There's an issue with each term having a certain linear combination of like.
I'm not sure. Yeah, I'm not sure it's easier to write it in form of matrix. Yeah, maybe once it is like this, yes, you can write it as a matrix, but yeah, it is. If you represent this vector with n entries, oh no, but wait, this is indeed a matrix. Oh no, but there is a mistake. Wait. There cannot be a mixture. Sorry, I did a mistake. This second line is not correct. I need to have everything in terms of I. So this is beta. Yes, 1 minus iota I times the sum j alpha ij iota j.
Okay.
Yes, they are coupled because it takes into account the graph. The graph couple the different, either the different S entries or the different iota entries. But yeah, but this, so you have n equations here and n equations here. Now, can you write this with a matrix? And is it slightly better? You're right. This is a matrix applied to a vector, but then you need to say something about this. I'm not sure it's not linear. It's not a linear system.
Linear, and it feels like for every entry in like the overall matrix equation, you have to have another matrix that is coupled with the I vector again.
So I'm not sure that a matrix version of this is really better. You can try, but I doubt. Okay, so you have 2n system of equation. This is for the SI model. Now for SIR model, it's worse because it's no more decoupled. So yeah, but it's decoupled in these two lines. So, but you can guess the equation. So it's going to be the same for the first one. Yes, I sum aij iota j with sum over j. So the same thing for the first one. In fact, it's only the second one which is different. Iota derivative at xi, oh sorry, at I is beta si. Because now you can recover, and your probability to recover or the derivative of your probability to recover has two contributions. One, because you get people who are becoming sick, and one, because you recover. So the variation of this guy has two contributions. And R dot I, you have only the guy who recovers. So now you have 3n equations. 3n equations. And I don't think you can decouple them. I didn't try. Maybe somebody can try to simplify a little bit, but hard. Large problem. Of course, if you take n is equal to 3, and it's not completely trivial, or let's take 4, you can see what happens. So it's in fact quite interesting. You start with 1 infected guy and 3 non-infected one. And of course, it has to be random, so you will see different evolution, but you can see, and you can also find some simulator on internet. It stay like this for a while. Suddenly, a guy become infected. And when you have 2 infected, most probably very quickly, the other 2 will also become infected. This is what you can find. But it also depends on the geometry of the graph. For example, if your graph is a cyclic graph, you can directly guess what is going to happen. The evolution can only go in 2 directions, and so on. So the evolution depends now on the structure of the graph. Right? Yes, okay, good point. Adjacency matrix, time dependent, it exists. It's called, there is a name for random graphs. So now you have to, either you make it random, so the adjacency matrix become random itself, or it's deterministic. You can play, but yes, it exists. People have studied this kind of situation. Sometimes this is also called random graph or random forest. You have many names. But as I said, very quickly, you end up with big set of equations. So there is, and this is the final subject, there is one approach which is called the mean field approach. So I'm going to mention this. One way to solve this, it's called the mean field approach. It's an approximation, but we will see in which sense. So mean field approach. It's in a sense, it's an averaging process. So I'm going to call xi, which is still a function of t. It's a function of t. It's the random variable. I have not really introduced this. So if you have no idea about what it is, please try to guess a little bit. The random variable at vertex I, I'm taking only 3 values, taking values in the set either S, either I, either R. In fact, the picture I made before, it was like this. Either dot was yellow or red. It's because I can hardly represent on a dot. Yes, it would be possible. There is a certain probability that it is infected. There is another probability that it is susceptible. This is just one vertex. And a third probability, this is possible, representing the exact probability at each vertex. But I can also just have one random variable which takes 3 values, either it's susceptible or infected or recovered, with a certain probability, each of them. Right. Okay. Then So for each vertex, we have one random variable taking value either in the set, either the value S or the value I or the value R. And now we set, and this is a standard notation. Or let's start with S. I define this as a function of time. This is the sum over I of probability that xi of t is equal to S. And similarly, I of t is the sum over all I of probability of xi of t is I infected, and you can guess R of t is the sum over all I, the probability that xi of t has recovered. So I sum the probability on all vertices. So it means that this, I just write it for the first one, it represents the expected, oh no, wait. Yes, it's a sum of probability. So it represents the expected number of susceptible vertices. And you do the same for I. The second one is represents the expected number of infected vertices, and the same for R. So it means the sum of these three guys, the sum of these three numbers has to be equal to n. It implies that I plus, sorry, S first, S plus I plus R has to be equal to n for the SIR model. For the SI model, it's only the first two. Now, what is, I fix, I'm going to use AB, which can be S, I, or R. I don't want to write 9 possibilities, because if you have 2 random variables, each of them taking 3 values, you have 9. So I'm going to use AB for A is either SIR or B is either SIR. Can you guess the definition for AB? With the same ID, because I will need it. But now I have to take the graph into account. It's going to be the expectation of having connected one A and one B. So let me write the formula. It is the sum on I and J of Aij times the probability that xi of t is A, xj of t is B. Think about it. It's a probability that we have 2 vertices connected. So the connection is encoded into the Aij with 1 vertex A in the state A, 1 vertex in the state B at time t. So you can interpret this quantity, the expected, this quantity here is the expected number of vertices of type A connected to B. And the notion of connected is encoded into the adjacency matrix. Okay, what is the end of this game? Because I can continue. First observation. It's quite easy to see that AB is, this definition is equal to BA. Why? It's an undirected graph and this matrix is symmetric. So, but now I can define, and I will stop with, because I can go on forever. What is ABC? It's the sum over ijk of aij, ajk of probability that xi at time t is in the state A, x, this is I, xj is in the state B, xk, and t is in the state C. Right? And they are connected, but be careful now. In general, this is not equal to ACB. Because it's a configuration of 3 vertices, one of type A, one of type B, and one of type C, but it's not the same as ACB. Okay. So I have introduced with, this is called the function with 1 point, because it depends only on 1 point. This one is called a function with 2 points, and this is called a function with 3 points. And now what about the dynamics? What about the evolution in this framework? Evolution or dynamic? First, just for SI. For the SI model, so only two types of vertices. The evolution is given by S dot is minus beta. And can you guess why? Not you, Hevido, everybody else, but wait. Why this is a natural evolution in this system? Because look, the variation of S has to be related to the fact that S is next to I, because if S is not connected to I, if it is only connected to other S, there is no possibility of a change. So the variation of the number of susceptible is related the same coefficient times the number of S next to I, right? And the same, okay, this is the simplest model. The increase of the evolution of the number of infected is given by a coefficient times this number of S next to I. What about the SIR model? If the same idea, SIR model in this framework. So SIR for, this is 2 for SIR. Now the same I variation, no, it was S. S variation, the first one, is given by this minus beta SI. Then I variation is given by beta SI plus gamma or minus gamma times I, and R dot is gamma I. Indeed, in this model, the recovering is related to the number of infected times a certain coefficient. Okay, so we have 3 equations in this case, only 2 equations instead of 2n. Are we more happy? Are you more happy than before? Because you have only 3 equations or 2 equations. What is the problem? Vic? The point is, you know, this is indeed this guy which up here. Yeah, we don't have a evolution equation for it. So we have an evolution equation for these guys, but we don't have an evolution equation for this one. So we need to give an equation, otherwise you will not be able to solve this system. So I need a new equation for the evolution of SI. I continue with the SIR model. So we need an evolution equation. An evolution equation for SI. And what is the evolution equation for SI? So the variation of SI, I'm going to give you the solution. It's minus gamma times SI plus beta times SSI plus, oh no, minus. Can we understand this? I hope the answer is yes. Can we understand the evolution of SI? Yes. So SI means you have two vertices. One is safe, one is susceptible, the other one is infected. What is the possibilities of changing this? Either the infected guy is going to recover. So if this one recover, we are no more of the type SI. So if this one recover, this is the first coefficient. But now we have other possibility. Either this infected guy is going to infect the yellow one. So it has a beta probability with a factor minus beta times these quantities. But we have other things. If the yellow one is connected to another infected, it increases the probability that this one is going to become infected. So this new situation is here. And what is this one? This one is SSI. So we have Y, wait. Did I? SSI. Now I'm a little bit surprised by this guy because the I infecting this S is already here. Okay, I need to double check why we have SSI. Wait a second. Because if yes, too susceptible suddenly become infected by infected one. And this is why it's a positive. We had two SS. So these guys were first two SS, but one is infected by I. And then these SS become SI. So yes, this it's a positive contribution to S. S become Si. This is the IS, the S become infected by somebody from outside or by its colleague. So yeah, we have these 4 things. So this is an equation for Si derivative. But now you see the problem. In order to write this equation, I had to deal with function of 3 points. So if I write the full system, I need now also an equation for this. So we can continue forever. We can continue writing equations with more and more points, But of course, you are not going to do this forever, because if you do it forever, it means you are back to the 3n equations. So there is a trick. You are going to, up to now, I haven't simplified anything. I have not taken any approximation, but so you can write this equation, and in the notes, I have written additional equation, because you can also write the equation for SS like this. What is it? You can write for SR, what is the variation? So you can write all these equations, and it's not difficult. You just need to think about what can happen. But how do you stop? We stop. Now we finish here. We stop by it's called taking a closure. Taking a closure, which means it's an approximation. At a certain point, you do an approximation. And the simplest example of closure is the following one. We assume that the product ABC, again, ABC is replaced, they are replacing either S or I or R, is to take something of this form. It's product of AB times BC divided by probability of. So it means you express your function of 3 points as a product of 2 functions of 2 points and 1 function of 1 point. There are justifications, but this approximation depends on the graph. I depends on the graph. And in particular, it depends on the coefficient C, which is this clustering coefficient. Clustering coefficient. I don't know in which sense it goes. If you have a tightly or with a big coefficient, probably this approximation is not good. While if your coefficient, clustering coefficient, is very small, which means you have very few triangles, this approximation is better. So you can discuss, and people have discussed when this approximation is good or not, but it means if you take such an approximation, then you are going to replace these 2 by function of 2 points, and you end up with a system which is quite small. But you observe it's nonlinear. It's nonlinear because you are going to have product, while before it's still linear. So you transform a linear system into a nonlinear one, but of smaller size. Okay, so it's 8 now. We will finish here. It's an entire topic. In fact, one day I gave a course, a master course on this topic. If somebody is interested in this, please contact me, because it's possible that I will come back to this topic next semester or in 2 semesters. So if somebody is interested in epidemiology on graphs, you can always come back to me and I can tell you what I'm going to do. Okay. Yes, Heavy Do.
Doesn't it have two contributions SI? Should there be a two in front of it? Because two SI.
Some, okay, I don't want to check now. But yeah, you're right. Sometimes because of some symmetry, you have a coefficient 2. This is correct. I'm not sure in this case, or maybe I simply missed it. Okay. If there is a coefficient 2 somewhere, please correct it. Ask Hevido, he's expert.